Good morning, everybody. Let's begin. On Wednesday, you've got a homework assignment due that has 3 problems. And today in class, I'm going to give you some hints and kind of reminders on each of those 3 problems. Hopefully that'll streamline the amount of time it takes you to solve it. And then the other thing that I hope you're working on already is your network design and optimization for the design project phase 2. And as I talked about last week, your only submissions for phase 2 is a pair of PDF files, one being what your network performance is under the design condition of maximum peak flow, with all of the annotated information related to flow rates, pipe dimensions, like the length and diameter, elevation of the reservoir, and so on. So one map with it peak flow rate, and then another map showing what the system is doing at static, meaning 0 flow rate condition. So if you have any questions about that, let me know, or revisit the recording where I kind of illustrated what the annotations should look like. Today we're going to continue talking about some topics in Chapter 12, which is specific energy analysis. And so are there any questions about the announcements before we start talking about the homework hints? All right. Problem 1222 is the first problem that you've got on the list for Wednesday. And it asks you to find the change of the water surface elevation. So the water is going to change its elevation, and we want to find out how much the difference in elevation in the water surface is because of either a bed step down or a bed step up. So we've previously introduced this idea of flow per unit width. So that's the lowercase q, and flow per unit width is the big flow rate Q, which is units of cubic meters per second, divided by the width of the channel. So you can only calculate the flow per unit width when you have a rectangular channel. Otherwise, it doesn't have any meaning. But in this problem, it is rectangular. Another way to calculate flow per unit width is simply to multiply the velocity by the depth of flow. So either of those will give you the flow per unit width. And if you know the flow per unit width, then it becomes quite easy to determine the critical depth, y sub c, because that's the flow per unit width squared divided by g to the 1/3 power. And I gave you a big reminder and warning that this streamlined way to calculate the critical depth only applies when you've got a rectangular channel. And if you don't, then you should use that full version of the Froude number equation. All right, so with that foundation laid, the first thing that it's asking you to do is if there is a step up, in Part A, it's introducing the idea of a step up. Well, what we're going to do here is apply the specific energy equation, including the step up, which reduces the amount of energy that's available at location 2. So it's E1, meaning the depth and the velocity head at 1. So E1 minus the delta Z is equal to E2. And I hope it's easy for you to understand why there's less energy at 2 than there was at 1, because the water had to exert some energy in order to get up over this step. And so that takes energy away that used to be at 1 and is no longer going to be available at 2. So the specific energy at 2 is lower. So you'll know Y1, you know the velocity head at 1, the height of the step is given. We know the flow per unit width is the same because the big Q is the same and the width of the channel is the same. So the only unknown in this formula is Y2. And we've previously a couple of times seen that when we have a formula that looks like this, with the depth downstream being the unknown, it ends up being a cubic equation that we solve for the 3 roots. And then depending on conditions, we're being supercritical or subcritical upstream. That guides us on which of the 2 roots downstream, which of the roots downstream should be selected. So then when this asks for the change in the water surface elevation, what that's going to be is the depth upstream minus depth plus delta Z downstream. So if it's the water surface that we want to know how much the water surface is changing, then we have to be a little bit careful about simply measuring. It's not just the depths that is affecting the water surface. And so, you know, we have to use a common datum at 1 and 2 to find how the water surface depth has changed. And so Y1 implies that we're using the bottom of the upstream channel as our elevation datum. And so then at 2, it's going to be the depth plus the delta Z to find out how high is the water here above this line. So we want to find out, you know, the height of the water depth at 1, the height of the water depth at 2, and then the change is the difference between the two. So then, if you've got a step down, rather than subtracting energy that's available at location 2, it's adding energy. So the water's flowing along at 1, and then it gets more energy as it flows off the step. And so E2 is going to actually have more energy than there was at E1. So if we just look at the specific energy formula here, we know the depth at 1, we know the velocity head at 1, the delta Z is specified in the problem statement. So again, the only unknown will be Y2, which we plug in all the numbers, get a cubic equation, solve for the 3 roots. Of the 3 roots, one will be a negative number, which is immediately rejected. Then the remaining 2 positive values of that cubic equation, one is a supercritical root, one is a subcritical root, and the which you select depends on whether conditions were sub or supercritical upstream. And if I remember correctly, it was subcritical, so you're choosing the larger of the 2 depths in both cases. So that's just a refresher on some of the key ideas in problem 1222. And I think the important thing to remember is because it's a rectangular channel, it becomes pretty easy for us to calculate the critical depth. And remember, you can determine whether the flow at 1 is supercritical or subcritical, super or sub, by comparing the depth that's given to the critical depth. And if the depth at 1 is greater than the critical depth, that means it's subcritical conditions. And if the depth at 1 is less than the critical depth, then that means it's supercritical at location 1. So, before we move on from this problem, does anybody have any questions? The second problem on the assignment deals with a channel that's expanding. And we're going to look at this also on Wednesday. This is just, you know, maybe your first taste of it in the homework assignment. You've got a rectangular channel that is expanding, and what they characterize is a coefficient of expansion. And that's in some ways analogous to a local loss. If you'll think back to pipe flow, how we had both friction losses and local losses. Local losses had to do with things like fittings, bends in the pipe. And so expansions like this, where a coefficient is specified, it's a similar idea where a certain amount of energy is lost because of the expansion. So what we're given, this is a top view of the channel. We're looking down from above, and we can see the width of the channel initially is 5 feet, and it expands to being 10 feet wide. So water's flowing along, the channel gets wider, and we want to know, when the channel gets wider, how does the depth change? And, you know, without actually doing the calculations, without knowing, you might think that the water would always get shallower if the channel is getting wider. That may be kind of just like your intuition or your instinct, but actually it doesn't. It depends on whether conditions are supercritical or subcritical. Sometimes the water depth will get shallower, sometimes it'll get deeper when the channel width expands. So what you need to know in order to predict the downstream depth is specific energy analysis, where again, this notion of flow per unit width, which is big Q divided by the bottom width, flow per unit width will allow us to determine the critical depth. If we compare the given depth of 4 feet to the critical depth, we can know whether conditions are super or sub at the upstream location. You could also calculate the Froude number and determine whether the flow regime upstream is super or subcritical based on the Froude number is greater than 1, super. Froude number less than 1, subcritical. But the specific energy formula, when we have an expansion, looks like this. So, I mean, it's the same exact idea as what we were just looking at in the previous problem, where there's a certain amount of energy at location 1. So there was some energy upstream. Then a change occurred, which takes some of the energy out of the system. And then the remaining energy is split between the depth and the velocity head. So just to summarize that again, there was a certain amount of specific energy at 1. The depth and the velocity head was the energy that was at 1. Then you lost some specific energy due to the expansion. And that is this term. Now, this is a third way for us to think about velocity head. I've already introduced you to, of course, v squared divided by 2g. I mean, that was the first way that we thought of velocity head. And then I said that's the same as q squared divided by 2g a squared. And now here's a third way that we can calculate the velocity head. It's the flow per unit width squared divided by 2g times the depth squared. So how does this relate to that? We've just divided both the numerator and the denominator by b, the bottom width. So remember, q is big Q divided by b. And then if we have area squared divided by b, then that just gives it, wait a minute. So area is depth times b, and so we're basically canceling out the b out of both terms in the area and just left with the depth. So basically this is saying there was energy at 1 and some of the energy downstream went to the expansion, and what remains is split up between the depth and the velocity head. And so in this entire expression, the only unknown is y2, because the flow per unit width is going to still be known at 2. It's the same flow rate that we already had, q, big Q, divided by the new b. So this is important. Flow per unit width at 1 is not the same as the flow per unit width at 2, because there's different widths. Upstream, the channel was 5 feet wide. Downstream, the channel width was 10 feet. So you'll have different flow per unit widths upstream and downstream. So we'll have a cubic equation, and then which of the 3 roots to select? Reject the negative root, and then you've got a shallow depth and a deep depth. And if you have supercritical conditions upstream, then you'd choose the shallow of the 2 options. And if you had subcritical conditions upstream, then you'd choose the deeper depth at location 2. So if I remember correctly, in this problem, we had subcritical flow at 1. The channel gets wider, and the flow actually gets deeper because of that expansion. So it's not maybe what you'd just instinctively guess, but that's hydraulics for you. You actually have to do the calculations sometime to know how the water's going to react in a certain situation. So any questions on this problem? Last one. Problem 1227 is another problem similar to the first, where you've got bed steps. There's a question that's being asked is, how tall could the step be without causing the flow upstream to become choked? So here's how to interpret that. Basically what it means is, if you make delta Z big enough, you're going to force the flow over the step to be the critical depth. The critical depth is the most efficient depth for carrying a certain amount of flow with the least amount of specific energy. And if we make delta Z any taller than the depth that causes critical depth over that step, then what has to happen is that pooling has to occur upstream in order for enough energy to accumulate to make it over the obstacle. This is something we're going to do a deep dive on later, but the shallow dive that's good enough for this problem is just knowing calculate the critical depth at 2. So this is another rectangular channel, which makes it easy for us to determine the critical depth based on the flow per unit width squared divided by g to the 1/3 power. So you're given the velocity and the depth, and here's another way to determine flow per unit width. It's either flow rate divided by b, or it is depth times velocity. So in our case, they've given us the flow velocity at 1 and the depth at 1. So you know the flow per unit width. From that, you find the critical depth. So set the critical depth, set the depth at 2 equal to the critical depth. And if you look at the specific energy equation, then the only unknown is going to be delta Z. So let me just flip back to this other one. So here is a step up. So here's the formula that we had for a step up. Let me paste this into here. So here's a step up. We know the energy at 1. We know the depth at 2 is the critical depth. We know the specific energy at 2 because we know flow per unit width. We know the depth at 2. So delta Z is the only unknown in this problem, in part A at least. In part A, you're solving for the delta Z. In part B, they're saying, well, now what if the delta Z was actually half the height of what you just determined in part A? So now we're specifying the delta Z and we want to find the Y2. So then that's just a repeat of what you did in the first problem. Okay, so remember this video is going to be on YouTube, so as you're working on the homework assignment, if you get hung up, then you could revisit the video recording or stop by my office during my office hours. I'm happy to help you if you've got questions. Any questions before we move on? So, if we have subcritical conditions and a step up, then remember E1 can be thought of as how much energy is available to overcome that obstacle. The delta Z is an obstacle. And the specific energy is changing because some specific energy is being lost, and so the energy that's available at 2 is less than the amount of specific energy than there was at 1, in the amount of delta Z being the difference. But the total energy doesn't change. Look at this dashed line above the water surface, the total energy line, because the total energy takes into account the depth, the velocity head, and some elevation above a constant datum that is unchanging. Total energy is different from specific energy because specific energy is always measuring using the bottom of the channel as the starting point. For total energy, what we're using is a common datum at 1 and at 2. So we're saying, let's have the elevation be maybe sea level. Or let's make the elevation be the bottom of the first channel, and then at 2, we're still using that same elevation to calculate the total energy. So if we lose some velocity head and some depth because of a delta Z, you're not losing total energy because the delta Z is added to the total energy calculation. So here's the specific energy diagram, and remember that if we have a step up, then that is a reduction in the specific energy. So if we at location 1, we had depth 1, the way we use the specific energy diagram, we had an animation of this last time. We start at Y1, go over intercept the specific energy curve down to find out how much energy we've got. This is a graphical solution of what we could also do numerically. Delta Z reduces the specific energy here at location 2, and then we go back up, and there are 2 crossing points on the figure. So if conditions were subcritical before, then we use the upper of those 2 crossing points. Those are the alternate depths. The subcritical alternate depth and the supercritical alternate depth. Since we were subcritical at 1, we will be subcritical at 2, and then reflecting off of that curve over here to the y-axis, we find y2. So it's interesting. The new depth downstream is going to be shallower. And this is another one of those maybe counterintuitive things where you'd think if the water has to flow over an obstacle, maybe that would make it deeper downstream. But it's not. It's getting shallower downstream if the flow was subcritical. But if you had a step up and conditions were supercritical, then the opposite is true. It's not going to get shallower. It's going to get deeper in the downstream location. And let's take a look at the specific energy diagram just to convince ourselves of why it's going to be getting deeper. So here's our specific energy diagram. So starting at y1, which is the original depth upstream, we're going over, finding the point of intersection with the specific energy curve, down to find the intercept with the x-axis. And so this is how much specific energy we have at 1. Delta Z reduces the specific energy, back up to the curve, and of the 2 crossing points, we're choosing the shallower of the 2 crossing points because it was supercritical at 1. And then over to the y-axis, y2 is a deeper depth than y1 was. Because conditions initially were supercritical, the water's actually going to get deeper after going up over that step. So we're in the supercritical range. The new depth is greater than the old depth. How did we know it was supercritical at 1? Look in the figure. See this little dashed line, YC? So what they were doing to determine the flow regime at 1 was comparing the depth at 1 to the critical depth. So this is something that's very simple to do. You don't have to even calculate the Froude number. You just look and see how does the actual given flow depth of y1 compare to the critical depth, which here was depicted just with a dashed line, the critical depth. So y1 was less than yc. That means it's supercritical flow upstream. All right. So let's take a look at some calculations having to do with what if water is flowing up over a step and what will be the flow depth after the step. Just we've seen this already twice when we're kind of talking about the homework problems, but let's look at some actual calculations here. If the channel is 10 feet wide, you can see it's rectangular, which we're always happy if it's a rectangular channel because everything's easier to calculate. The critical depths are easier to calculate and so on. And it's a step up, so remember that the amount of specific energy at 2 is less than the specific energy at 1 because of the delta Z. So what will be the new flow depth after the step? So I'm not going to pause and have you do these calculations. Let's just look at them and see if the step-by-step approach is consistent with kind of the workflow that you're coming to understand. So in this problem, you were given the flow rate of 250 CFS and the bottom width of 10 feet. So with that, you can calculate the flow per unit width of 25 feet squared per second. And we care about that because we want to know the critical depth. And the flow depth at 1, we were told it was 5 feet deep. And if we compare that to the critical depth of 2.7 feet, since the flow depth of 5 feet is more than the critical depth, then the flow regime at 1 is subcritical. So how much specific energy was there at 1? There's the depth at 1 plus the velocity head at 1. And so combining the two together, 5.388 feet of specific energy at 1. And then the energy at 2 is going to be the energy at 1 minus the losses. So let me just write this on the board, because whether we have the delta z on the left-hand side or the right-hand side of the equation changes whether we say plus delta z or minus delta z. So E1 minus delta z equals E2. This is for a step up. So the specific energy at 2 is less than the specific energy at 1 in the amount of delta z. So the other way to say that is the energy at 1 is equal to the delta z plus E2. That's the same thing. I just moved the delta z to the right-hand side of the equation. So that's what this is. This is saying the energy at 1 plus the depth and velocity head at 2 plus the delta z. So just accounting for all of the energy. So E1 was 5.388. Then if we have 5.388 minus 0.5, then what's left is on the left-hand side of the equation, 4.888 feet. So this is the energy available after the step up, and it's going to be in the depth and the velocity head. So that velocity head term could be V2 squared divided by 2g. It's not that, because we don't know V2. It could be q squared divided by 2ga squared. And then the third way that we're thinking about velocity head these days is q squared divided by 2g y2 squared. And that's what we're doing to get this 9.705. That's just what's left in the numerator after we cancel out the 2g in the denominator. So cubic equation, solve for the roots, and the negative one we immediately reject. There's a supercritical root and a subcritical root, and of those two, because flow conditions at 1 were subcritical, then that means we choose the larger of the two depths for the downstream depth. So 4.383 feet. So that's the same process you're going to go through for the first problem and the second part of the third problem on the homework assignment. Okay, so if we have critical conditions, then the Froude number is equal to 1. And if we have a rectangular channel, we can determine the critical depth with flow per unit width squared divided by g to the 1/3 power. Now here's an interesting thing, is that when conditions are critical, the flow depth represents 2/3 of the specific energy that exists. It's a simplification that we're going to use to our benefit in simplifying calculations where we won't bother calculating the velocity head. If we know that the flow conditions are critical and it's a rectangular channel, then that means the specific energy is just equal to 3/2 times the critical depth. It's a lovely simplification. So water depth is 2/3 of the specific energy. Now let me just give you kind of a numerical proof to give you confidence in that statement and to illustrate the significance of it. Like, what does it mean that the water depth is 2/3 of the specific energy? A lot of the time we want to know how much specific energy is there, because in all the problems that I've given you hints on today, for example, we have to know how much specific energy is there at a location in order to know, like, the new depth downstream, for example. So let's just take a rectangular channel that's 50 cubic meters per second, and it's going through a 5-meter wide rectangular channel. So let me illustrate some calculations that I think will help you to understand, like, who cares if the specific energy is 3/2 times the critical depth. So if we have 50 cubic meters per second and the channel is 5 meters wide, then obviously that means the flow per unit width is 10 meters squared per second. So put that into the critical depth equation, and you can see that the resulting critical depth is 168 meters. Okay, so far so good. So I'm saying that if you know the critical depth and it's a rectangular channel like this is, all you have to do to find the specific energy is just 1.5 times the critical depth, or 3/2 times the critical depth, and that will tell you how much specific energy there is. So E at a location where you've got critical flow in a rectangular channel is 1.5 times the critical depth. And if it's this easy to calculate the critical depth, then that's a pretty easy way to calculate the specific energy for a rectangular channel with critical flow. So let's just prove it to ourselves that that actually is true, that this isn't just something that's been made up. So the other way to know for sure is let's see what is the velocity head if we had 50 cubic meters per second going through a channel that is 5 meters wide and the flow depth is this critical depth of 2.168 meters. So if that was the case, then your velocity would be 4.613 meters per second. And so the depth component of specific energy is 2.168. The velocity component of the velocity head, so the velocity head is 1.084 meters. So collectively, those two components added together, it's the same 3.252 meters of specific energy. So there will be times when it's really easy to calculate the critical depth, but it's harder to know just at a glance what is the velocity head. So this is a nice shortcut. So keep this shortcut in mind if you've got critical conditions and a rectangular channel. Then all you need to do is find the critical depth and multiply it by 3/2 to know what is the specific energy. The same thing is true. The reverse is true. So if it's 3/2 times the critical depth to get the specific energy, if you know the specific energy, then you can find the critical depth for a rectangular channel just by multiplying it by 2/3. So we'll use this from time to time, this simplification. So just to review, if you've got a step down, which you do on one of the homework problems, then the energy at 2 is the energy at 1 plus delta Z. So that's saying that some energy has been gained as the water's flowing downstream. So there's going to be more energy at 2 than there was at 1 in the case of a step down. In the case of a step up, there will be less energy at 2 than there was at 1 because of the step. So specific energy says depth plus velocity head plus the delta Z is equal to depth and velocity head at 2. We can express the velocity head in terms of Q and A, or flow per unit width squared divided by 2GY squared. We're getting a larger and larger tool chest of these shortcuts and expressions we can use with the specific energy equation. So let's say it was a little step. What if water's flowing along and there's just this little step? And let's say that it was subcritical at 1. So if it was subcritical, it's going to make it a little bit shallower at 2. But if it's a small step, it won't be much shallower as the water flows up over that step. But then what if we made delta Z a little bit bigger? So delta Z was a little bit bigger, then that will bring Y2 down more. So there's a limit to how big it can get, and the limit is some critical step height. So delta Z critical is the step height that forces critical flow conditions at location 2. So if we keep making the delta Z bigger and bigger and bigger, eventually you're going to force critical flow conditions at 2. And if you made the delta Z even bigger than this, then the water wouldn't have enough energy to get over the step. And it would have to start pooling at 1. And by pooling, what I mean is getting deeper. The water would have to get deeper at 1 to accumulate enough energy to get up over the step. If we make the delta Z larger than the critical height, then there's going to be a new flow depth. So in this diagram, this is showing with the dashed line what the initial or original depth was, Y1. And if we made delta Z bigger than the critical step height, then what happens is that the water depth will increase to Y prime 1. That's the new upstream depth, until there's sufficient specific energy to cause critical flow conditions downstream. So it was critical at the critical step height. Then we made the step even bigger. It's going to stay critical flow downstream, but in order to achieve critical flow downstream, the water depth would have to get deeper at 1 in order for enough energy to accumulate to get up over this larger step. So the flow would back up. It would temporarily be unsteady, meaning conditions are changing over time. The flow in does not equal the flow out through a control volume for this period where the water is pooling upstream. So we'll do a deep dive on how do you calculate the new depth. You know, if your delta Z is larger than the critical step height, how do you determine what will be the new depth upstream? We will do that. But for today, let's just remember that when you've got critical conditions, the water depth is 2/3 of the specific energy. The velocity head is 1/3 of the specific energy at that point where the conditions are critical. So here's the specific energy diagram showing those successively larger delta Z's. Like our initial specific energy at 1 had 2 alternate depths, and we were subcritical. So this was our initial depth, Y1. And then we had a step up, which reduces how much specific energy you've gotten. So there was Y2, which was associated with this delta ZA. And then we made the delta Z a little bit bigger, so we had even less specific energy. So this delta ZC, the critical step height, was what's the maximum step that you can make when you have a starting amount of specific energy to get to the far left side of the specific energy diagram. This location that's associated with the critical depth. And if we go beyond that, we're not on the specific energy diagram anymore. And so that means that there isn't a depth that is associated with a step height of delta ZD. That we need more energy and a different specific energy diagram to find out what the flow conditions are going to be like. So a step larger than the critical step is going to cause pooling. So it's going to get deeper upstream. The flow will back up. So the water is, you can think of it as clogging, temporary clogging in the vicinity of the step. If you have this obstacle, and I mean, it makes perfect sense. If we went into the hydraulics lab, there's a flume in there. It's just a rectangular channel. If we went into the hydraulics lab, and maybe we'll do that. We won't do it next week because you'll be on spring break next week. So the flume has a bottom and plastic sides, right? So if water's flowing along in the flume, normally it'll just go out the bottom like this. But there's these little plastic pieces that I can slide in here. There's kind of like a tray holder. And so if I dropped in a big plastic barrier into this location, and the water used to be flowing over the edge, and I dropped in that plastic barrier, well, obviously what's going to happen? The water's going to rise until there's enough energy to flow over that obstacle. So this is an extreme case of the same thing with this delta z. Is if you make the delta z high enough, then there isn't enough energy in the existing flow depth to overcome the obstacle. And so pooling will occur. So the flow will back up and continue to get deeper until there's just barely enough energy to get over the obstacle. And the minimum amount of energy at 1 to flow over the obstacle is that depth which is associated with critical conditions. So here we've got some new notation. Y1 was the original depth prior to the flow encountering this excessively tall step. And then Y prime 1 is the new depth after the pooling. And it'll be the new depth once you reach a new equilibrium. Because it's going to start, like 1 microsecond later after we suddenly introduce this step. It's just going to get a little higher, and a little higher, and a little higher. But eventually, it'll come to an equilibrium. And equilibrium meaning that it's going to resume steady flow. The flow in and flow out through this control volume that we're looking at will be equal. And so the new normal, so to speak, that new flow depth. And so let's say that we had water flowing this rectangular channel and we wanted to find out what's the maximum step height. Excuse me. Let's just, we've already a couple of times today already looked at what we do when we have a known step height. What do the calculations look like when we are trying to find the maximum step height that occurs prior to choking? Let me jump into these calculations just to show you the maximum step height. So at location 1, the channel was 2.5 meters wide, 0.9 meters deep. It's still 2.5 meters wide. Downstream at 2, we're trying to find out what's the maximum step height. So we know it's 4.25 cubic meters per second going through there. And since we know the depth and the width at 1, I can calculate the velocity at 1, which will be useful for the velocity head. And then at 2, I don't know the velocity yet at 2 because I don't know how deep the water is. But I can express the velocity head in terms of the flow per unit width because it's still going to be 2.5 meters wide and it's still going to be 4.25 cubic meters per second. So I've got the flow per unit width at 2, which I'm going to use to find the velocity head at 2. So I'm going to skip over part A because that's not as interesting as this question of what's the maximum step height prior to choking. So the maximum step height is, we're saying let the depth downstream at location 2 be the critical depth. So calculate the critical depth based on the flow per unit width. So we get a critical depth of 0.665. And then we're saying that we're letting the depth be the critical depth, and the velocity head will be the velocity that's associated with a depth of 0.665. So we know the energy at 1, both the depth and the velocity head. We know the energy at 2, both the depth and the velocity head. And the only thing that's unknown in a case like that is the delta z. So this is really similar to the homework assignment you've got where in the specific energy equation, I guess for once we're not solving for a cubic root because we don't have to. It's not the depth that's the unknown here. It's what's the delta z, the maximum delta z that could occur prior to choking. So any questions about that step-by-step process you should follow when you're trying to find out the maximum step height that can be tolerated prior to choking? And by choked flow, any kind of a constriction that's too much for the specific energy to handle is what we'd call choked flow. So it could be like a channel that has a step that's too large, Or it could be a channel if it's contracting, like if the channel is getting narrower, if it becomes too narrow, that could also cause choked flow. There isn't anything where the channel would get too wide and cause choked flow. That won't cause choking. But if the channel becomes too narrow, it is possible that you could have choked flow from that. So if you exceed some maximum constriction, then choked flow can occur. And the reason why that's a problem is if the water upstream is getting deeper, it could cause flooding. It could cause the water to go out of the channel banks. It could cause homes that are adjacent to a creek, for example, to become flooded. So think about if you've ever lived in a rural area before, you know, sometimes people will put in their own culverts to have the driveway go from one side of the creek to the other. And some people are, you know, belt and suspenders types where they don't want to take any chances. They want to be really cautious. And there's somebody on my road who has a gigantic metal culvert. I mean, like the creek is probably 5 feet wide and this culvert is 5 feet wide. Like it is enormous. So they don't want it to ever be the cause of choked flow, but some people are trying to save a little bit of money. They'll maybe put a much smaller culvert, like 2-foot diameter. Most of the time when it hasn't been rainy, water will flow through that culvert no problem. But if you've got a big storm going through, then the people with a culvert that's too small could be the cause of choked flow. And the water levels could rise because water isn't able to pass through that culvert fast enough, and then it backs up upstream. So they could inadvertently cause damage to their neighbor's property by having an undersized culvert. So there are some like real world risks associated with choked flow. When we want to calculate the new upstream depth, the process we're going to go through, we've only got a couple of minutes left, but the process we're going to go through is saying, you know, this is what it looked like before there was some obstacle, but some obstacle was dropped into the stream. Let's say just at the extreme end of the example, what if this new obstacle was the same height as the water? So the water depth is going to increase upstream, and that's what we want to find out, is how deep does it have to get to flow over this new obstacle. So that's where we're going to leave it today. When we get together in class on Wednesday, we're going to calculate that new upstream depth, y'1. So I will see you on Wednesday.